Hello, I'm Jiatou Ding. My report is about versatile bipedal locomotion. Our work focused on versatile walking, which is highly designed for humanoid robots to operate in real-world environment. The locomotion versatility demands robustness against dynamic disturbances, including modern errors and external pushes. Besides, the locomotion versatility also demands adaptability to different walking tasks, such as climbing stairs and larger stairs up. To this end, let's imagine a push-recover scenario. The robot will need to adjust the ankle torques to maintain balance. Besides, to enlarge the support region, the robot may need to change the step location in real time. In other cases, such as large step up, the robot has to rotate the upper body parts to adjust the angular momentum. Furthermore, vertical motion is required to accommodate the height variation. That's to say, to realize versatile walking in real-world environments, the robot needs to adopt various balance strategies. However, it's still a big challenge to integrate the ankle, stepping, hip, and height various strategies in a unified and time-efficient way. To solve this problem, in this work, we use a nonlinear inverted pendulum plus flywheel model to characterize the working dynamics. As a result, the nonlinear center of pressure dynamics is determined. By manipulating the COP movement, the ankle strategy can be used. Since the vertical acceleration is considered here, the height variation can be realized very easily. Note the flywheel is added here for modeling the angular momentum. Assuming the constant inertia tensor, the change in the angular momentum can be characterized by the rotation of upper body. Then, the nonlinear model predictive framework is employed here for online gate generation. Since the approach is run in a closed-loop manner, we can also take the MPC as a tracking controller. Different from the previous work, we propose to use the acceleration of each motion component as the control input. Since we aim at integrating all the above-mentioned strategies, the design variables consist of center of mass acceleration, angular acceleration, step location, and COP relaxation variables. And we attempt to minimize the tracking errors of the center of mass position, upper body rotation angles, and the step locations, while regulating the velocity of each motion channel. Besides, the control inputs are also penalized. In this way, the vertical height, upper body rotation angles, and the step locations can be modulated simultaneously. To achieve the feasible working pattern, the stability and the physical constraints are considered here. Here, we introduce the hybrid stability constraints. Firstly, we restrict the COP movement within the support region formed by the support field. In this way, the ankle strategy is integrated for rejecting external disturbances. However, different from traditional work, this work uses a soft COP constraint by introducing select variables. In this way, we can enhance the robot mobility and the MPC solvability. As a complementary, we limit the distance between the final DCM of each step and the next step location. In this case, the one-step capture conditions are used here for rejecting external disturbances. As a result, the whole problem can be formulated as a quadratic constraint quadratic programming program, where the sequential quadratic programming technique is employed here to get the solution. In this numerical simulation, the work pattern with much higher step frequency, 0.2 seconds per step, is designed for the robot with a point field. Since only the point contact exists, the support region shrink. When using the high COP constraint, the feasible trajectory cannot be obtained. It can be seen from the figure on the top. On the contrary, the enhanced MPC strategy can generate a feasible trajectory by relaxing the COP movement. By doing so, the COP may deviate from the contact center. However, since the one-step capturability is bad, we believe that the trajectory is feasible for the fast locomotion, which would also be demonstrated by the dynamic simulation. In the dynamic simulation, the robot equipped with the final side fit is first used. To verify effectiveness, comparison studies are first conducted, where the robot is expected to recover from external disturbances when stepping in place. In this case, the horizontal external force is applied to the pelvis. We can find more balanced strategies are needed as the push force rises. That's to say, the integration of multiple balance strategies contributes to higher robustness. Then, the robot is designed to work across step stones while rejecting push forces. We can see that due to the utilization of hip strategy, the robot accomplishes the working task without losing balance. More experiments have also been conducted on a robot with a point feet. In the first scenario, due to the utilization of COP and DCM constraint, the robot can also maintain balance against external pushes. Then, in the second case, the robot is designed to work in the 3D scenario. By integrating the hip and height variation strategies, the robot with point feet can also maintain balance. Finally, we compare the current work with the previous one. We found that we have improved the time efficiency by enhancing the MPC formulation. At the conclusion, our contribution is threefold. Firstly, multiple balance strategies are integrated in a unified nonlinear MPC framework. Secondly, hybrid stability constraints are adopted here for the robot with a finite side feet or point feet. Thirdly, time-efficient solution is achieved for a real-time application. The future work can be done from following aspects. The first is to try to integrate the modulation of step duration by using the hierarchic optimization technique. The second is try to get the global optimum of the QCQP program by using the semi-definite relaxation technique. So that's all. Thanks for your attention.